Yes. Okay, thank you very much. And also I'd like to thank the organizers for the kind invitation to this beautiful place and this wonderful conference. So I'm one of these unusual people who come here from a chemistry department. So chemistry is what I will be talking about. To be more specific, chemistry between cold ions and cold neutrals. So the technology that we use in all of our experiments is to produce ensembles of cold ions in a radio frequency ion trap which form ordered structures, so-called Coulomb crystals. And what you see here is a Coulomb crystal of laser-cooled calcium ions in our ion trap. So there's a fluorescence which is generated from the laser cooling fluorescence of these laser-cooled ions. You can also put molecular ions into the trap and then use the atomic ions to sympathetically cool the molecular ions, and then we get what we call a bicrystal, a molecular Coulomb crystal, where we have molecular ions cooled into the center of these calcium Coulomb crystals, seen here by this non-fluorescent area in the center of this crystal. So what do we use? So what do we use these kind of Coulomb crystals for? So we are interested in studying ion chemistry in a new physical regime, so at very low collision energies, primarily to study exotic chemical processes at low temperatures. And also ultimately we would like to study, like every cold chemist, the quantum character of ion-neutral collisions. But also what I would also like to highlight in this talk is that this technology enables us to generally perform chemical reaction experiments under extremely controlled conditions, so allowing accurate quantum state and collision energy control in chemical experiments. And also, since one can observe single ions in these Coulomb crystals, we can perform chemical reactions with single localized particles. So what I will be talking about over the next half an hour is where I will first highlight some recent results on light-assisted chemical reactions between laser-cooled ions and atoms. Then I will talk about reactions with molecular ions down to about 20 millikelvin. And then I will switch gears and talk about controlled chemistry experiments with Coulomb crystallized ions. First about fully state and energy selected reactions using these Coulomb crystals. And secondly, about, if time permits, about the new experiments where we study reactions with selected conformers in the gas phase using basically the same technology. So let me start with cold chemistry. So the method that we use here, our cold chemical reactor, if you will, is a so-called hybrid trap. It's a combination of a trap for ultra-cold atoms with a radio frequency ion trap. It has first been proposed by Winthrop Smith in about 2003. And we're actually not the only ones who do these sort of experiments. There are a range of different hybrid trapping experiments in operation worldwide at the moment, at MIT, in Cambridge, in Ulm, Connecticut, at the Raman Research Institute, at UCLA, and actually many more are coming online. So this is really an emerging field at the moment. We will have many more hybrid trap talks during this conference a bit later on. So our hybrid trap is a magneto-optical trap for 87 rubidium atoms superimposed on a linear radio frequency ion trap to trap and laser cool atomic and molecular ions. So we superimpose these two traps, and then we study interactions between the atoms and the ions. So in the experiment, it looks like this. So what you see here is a combined fluorescence image of both the atoms and the ions in the trap. So this is again a Coulomb crystal of calcium ions in a sea of ultra-cold rubidium atoms in the MOT. So just to give you an idea, so the thermal energies of these ions are on the order of 10 millikelvin. Those of the atoms are on the order of 100 to 200 microkelvin. So these are the kind of energies that we are dealing with here. So once we do this, once we overlap these two species in our experiment, then we see the following. So this is a fluorescence image just of the ions. We have blocked out the fluorescence of the neutrals with a color filter, so to only look at the ions. And we see that this Coulomb crystal shrinks. So this means that the calcium ions react away on a time scale on the order of about 2 minutes. So what is going on here in this experiment? So we are chemists, and every good chemist first asks the questions, okay, there's a chemical reaction, what are the products? So to answer this, we turn our ion trap into a mass spectrometer and to figure out what kind of products we form in this reaction. And we see that, in fact, after this reaction, we observe 4 different species in the trap. First, we have calcium ions left, right? This is what we started off with. Then we have rubidium ions. Yeah, so this is a kind of a product that forms in a charge transfer reaction when an electron hops over from the rubidium to the calcium. And then, to our surprise, we found calcium rubidium ions and rubidium-2 ions. And this was a bit surprising because the densities in our trap are so low that we do not have any ternary processes which could stabilize a molecular product collisionally in this environment. So at this point, we started to scratch our heads and realized that there's really little known about these calcium rubidium systems. And then we contacted our good colleagues, theoreticians, to be more specific, our chairman, Olivier Doulieu, and his team. And they started to calculate the potential energy curves of this calcium rubidium molecule for us. And this actually already allowed us to understand a bit more about what is going on. So as it turns out, the lowest energy collision channel that we are observing, so this is rubidium in its ground state and calcium in its ground state, is not the lowest state of the molecule. There are other states below, and in particular we have a triplet pi state on the molecular triplet pi molecular curve which crosses the singlet sigma entrance curve of the lowest collision channel. So we have here non-adiabatic couplings between these two curves. So the system can hop over to this triplet pi curve and then depart again, connecting to a charge transfer asymptote where the charge has hopped over from the calcium to the rubidium. So this explains part of the signal of rubidium plus that we observe in the experiments. But there is more. There is another state below, the absolute ground state, and this actually can be reached from our entrance channel in a radiative transition. So the system emits a photon, and if it populates a bound vibrational state on the lowest curve, then we actually form a bound molecule. This process is called radiative association. Or if we populate a continuum state, then we get charge transfer again, and in this case it's radiative charge transfer. So this explains why we observe calcium rubidium molecules, and then the rubidium-2 plus molecule is probably a consecutive product of calcium rubidium plus with rubidium in our mod. So this explains the products that we see, but there is actually more to this. So both species in our hybrid trap are laser cooled. The ions are laser cooled, the atoms in the mod are laser cooled. So we always have population in excited states. And we can change this population by changing the laser cooling conditions. And what we find is that in particular, the excited state of calcium play a big role. So calcium has an excited doublet P1 half state, which we access in laser cooling. It's a doublet T3 half state, which is also involved. And what we find is if we change these populations and measure the rate constants, is that especially the rate for reactions between calcium and doublet P1 half with rubidium in its ground state is actually dominates the kinetics that we observe in this experiment by 2 orders of magnitude. So what is going on here? So qualitatively, this can also be understood by using these quantum chemical calculations. So this entrance channel, rubidium in its ground state with calcium plus in the 4p state, is already at quite a high excitation energy. And here we find that we have a high density of electronic states, and this high density of electronic states just offers various opportunities for non-adiabatic charge transfer processes and also radiative processes connecting to the lower lying molecular states. So this gives us a qualitative explanation why these processes appear to be so fast in the highest channel that we observe. So we observe the formation of molecular ions by radiative processes in these experiments. We observe acceleration of these reactions by electronic excitation. And it's a fair question to ask, is this only specific to calcium rubidium, or is this also observed in other systems? And to shed light on these questions, we have recently studied another system, barium plus rubidium. There's actually some work by Johannes Hecker-Denschlag's group, which preceded this, where they looked at collisions in the absolute ground state. Here, again, we looked at light-assisted processes involving excited states of these species. So the difference, just looking at the potential energy curves between calcium plus rubidium and barium plus rubidium, can already be appreciated by looking at these diagrams. So for calcium plus rubidium, for the lowest channel, we had these 3 processes: non-radiative charge transfer, radiative charge transfer, and radiative association. If one looks at the curves for barium rubidium plus, then one immediately sees that the triplet pi state, which gives rise to non-radiative charge transfer and calcium plus rubidium, connects to a higher lying asymptote in barium plus rubidium. So this non-radiative charge transfer channel associated with this molecular curve is energetically closed. So we only have radiative processes possible if we look at the lowest collision channel in the barium plus rubidium system. So what do we observe in the experiments? So this is a Coulomb crystal of barium ions where we laser cool the 138 barium species. So there are other isotopes present which are not laser cooled and are hence dark. So before the experiment, then we switch on the mod, overlap it with the Coulomb crystal. And after the experiment, we see something like this. So the barium has reacted away, and we see dark areas which correspond to sympathetically cooled molecular ions formed. So the mass spectrum again tells us we have two products in this case, rubidium plus, charge transfer products. And again, we see a peak corresponding to barium, rubidium plus, the molecules. And in this particular case, we can directly see them in the experiment. So this is a simulation of this crystal using molecular dynamics methods. So in the center, we have the rubidium plus product, right, which is lighter than the barium plus and is therefore cooled into the center of a Coulomb crystal. And we also see the heavier molecular product, right, sympathetically cooled to the outside of the Coulomb crystal, right, which can be seen by this characteristic flattening of the crystal. So this is a direct indication that a visual indication that we form molecules in this experiment. So to compare this with calcium plus rubidium, we find that the rates are generally the rate constants are generally about an order of magnitude lower in the different channels compared to calcium plus rubidium. Interestingly, in barium plus rubidium, the channel where we have barium in the ground state and rubidium in the doublet P3 half state is the one with the largest rate constant. Yeah? Whereas in calcium plus rubidium, this didn't play any significant role. Okay, so an interesting question in this whole context is, of course, how do these rates scale with the collision energy? How do they depend on the collision energy? And so we have a trap experiment, and in a trap experiment, it's notoriously challenging to change collision energies. But in these types of experiments, there's actually an easy way how one can do this. Namely, these radio frequency ion traps that we use, they use radio frequency field to confine the ions. And these time-dependent fields constantly pull and push the ions backwards and forwards. And this is called the micromotion. And the energy that's stored in this micromotion depends on where the ion is located in the trap. So ions which are further away from the trap axis have more micromotion energy than ions which are close to the central trap axis, where the micromotion energy actually vanishes. So this means that large crystals like this one have on average a higher ion kinetic energy than small crystals or even single ions which are all neatly located on the trap axis. So basically we did these experiments with ion crystals of different sizes. With molecular dynamics techniques, we can, and comparing the simulations with the experiment, we can work out the collision energy distributions for these different crystals in the trap. So there's a double logarithmic representation of these collision energy distributions that are generated by these crystals. And then what we get is a rate constant as a function of the average collision energy in the range from about 20 millikelvin to 20 Kelvin. And what we find is that there is essentially not a significant dependence. So the rate constant as a function of the collision energy is basically flat. So how can one understand this? And again, there our theory colleagues help. So what you see here are cross-sections for calcium plus rubidium for the lowest reaction channel, so rubidium in its ground state reacting with calcium in its ground state, for the non-radiative charge transfer. This was calculated by Franco Cianturco and his group and published about almost 2 years ago. And these are the radiative cross-sections, so the cross-sections for the radiative channels, radiative charge transfer, and radiative association for the lowest collision channel calculated by Olivier and his team. So two things are noteworthy here. The first thing is you see this pronounced resonance structure in the cross-sections, and these are shape resonances, and they appear for all three processes. And first, if you look closely, if you disregard these resonances for a moment, and you see the slope of this baseline is very, very similar. Yeah, I will come back to this a bit later. So what we can do now is we can take these results, right, and velocity average them over the velocity distributions of our ions or of our for the collision velocities to get the rate constants. Yeah, and this is what is shown here. So these are the results. The black line is the sum of all three processes. The star is the experimental result at about 2 Kelvin, and one can see that this is the right order of magnitude. Let's put it that way. So this is all for the lowest channel, mind you. And here I remind you again of the result of the experiment. And just to emphasize again, this is averaged over all channels. Yeah? In particularly, the calcium plus 4p plus rubidium 5s channel contributes dominantly to this result here. So in a way, we are comparing apples and pears here, but the interesting thing is that the apples very much look like the pears. Yeah. So we have so for the lowest channel theory predicts this flat dependence of the rate constant on the collision energy, which we observe in the channel averaged experiment. Yeah. The magnitude of the rate constant is different, of course, right? Because here the 4p channel, calcium plus 4p channel, predominantly contributes. So I will come back to this point in a minute again, just to compare this with barium plus rubidium. Barium plus rubidium, we see again in the experiment a very flat dependence of the rate constant on the average collision energy. These are again for the lowest channel, the radiative cross section, for radiative association and radiative charge transfer. Again, we see this resonance structure. And again, if we convolute this or velocity average this with our collision velocity distributions, then we again get rate constants for these processes, which are predicted to be essentially flat with collision energy. So how can we understand this? So let me just briefly summarize what we observe, right? So the rate constants are essentially constant with the collision energy. And the energy dependence of the rate constants, but not their magnitude, of course, seems to be similar across all channels that we sample in the experiment. Yeah? All of them seem to contribute, so those that contribute seem to give rise to this flat dependence of the rate constant on the collision energy. So what is going on here? So if you just disregard these shape resonances in the cross sections for a moment, then what we see in the calculations is that the energy dependence of the cross section can basically be described by classical dynamics. So in the calculations, which are purely quantum mechanical, we basically recover a classical behavior in the sense that the reaction only proceeds if the centrifugal barrier is overcome. Yeah? And from classical collision theory, if we have an ion-neutral collision with a potential that scales in the long range with r to the minus 4, and this is the case for all the relevant channels contributing to our rate constant, then which basically get the classical Langevin capture picture that the rate constant is constant with energy. So this seems to explain this flat dependence of the rate constant of the energy. It's more or less Langevin dynamics. So, but the magnitude of the rate constant, so not the relative dependence on the energy, but the magnitude of the rate constant is of course determined by short-range, non-adiabatic and radiative couplings, as I've explained before. And what we see in the calculations is that these coupling matrix are essentially, in our case, independent of the collision energy. As long as the collision energy is low, and as long these couplings are all localized in a deep potential well, which is deeper than the asymptotic energy. So this seems to be the reason for this behavior that we are seeing, and we have discussed this actually in great length in a paper that can be found on the archive at the moment. Okay, now let me come to a molecular system now, leaving atomic ions behind. So we have recently performed a study where we have sympathetically cooled nitrogen ions into a Coulomb crystal and reacted them with ultra-cold rubidium atoms in our trap. And so with this kind of techniques, we were able to reach collision energies on the order of 20 millikelvin. And to our knowledge, these are kind of the coldest reaction experiments that have been performed with molecular ions thus far. So I will tell you a bit later how we produce these molecular ions. So for the moment, suffice to say that we produce them. We sympathetically cool them into the Coulomb crystal. You can see them as a non-fluorescing ribbon in the center of these crystals. Then we switch on the MOT, and they start to react away quite fast, actually. One can see that they disappear. This ribbon disappears from the center of the crystal, and in the simulation, we can make product ions visible again, and then we see that we form some sort of product here. So the product is, again, as identified by mass spectrometry, is rubidium plus. So we again have a charge transfer reaction going on here. So what is quite remarkable in this system is that, so the nitrogen ions, they are, of course, only sympathetically cooled, so they are all in the ground state. But the rubidium atoms are laser cooled. And what we find is that we have a strong dependence of the rate constant on the population in the rubidium doublet P3 half state, which is the upper state of our laser cooling transition. So, and if we can work out the state-specific rate constants, and we find that in this excited channel, actually the rate constant is more than 2 orders of magnitude larger than in the lower channel. So what is going on here? So it's actually been known from previous studies with fast ion beams that these sort of reactions, these charge transfer reactions, are most efficient if the entrance channel is in resonance with a product channel. So what does this mean? So we start off with nitrogen ions in the ground state, and in this case rubidium in this excited WB3 half state. And then we have product channels forming rubidium plus in its ground state and nitrogen in low Rydberg states, which basically have the same energy as our entrance channel. It has been shown before that under these conditions, these reactions are very fast. However, for the lowest channel, we don't have such a condition, and for this reason, the reaction is quite slow. But there is a bit more to that, actually. If one looks at the rate constant for this excited channel, then it's on the order of 2 times 10 to the minus 8 cubic centimeters per second. This, at least for me, this is the fastest rate constant that I have ever seen. And one can compare this with a Langevin rate constant for this system. So just from the Langevin capture model that I have discussed before, so charge-induced dipole interaction is a factor of 4 smaller. So what's the reason? So what's going on here? So one realizes that rubidium actually has, in this WP3 half state, has a permanent quadrupole moment. And this permanent quadrupole moment can, of course, interact with the ion. So we get we of course have a charge-induced dipole interaction, but then we have a charge quadrupole interaction. And what we did is we just put this into a simple classical capture model, right, in the spirit of Langevin, but just adding this charge quadrupole interaction. Calculated the cross-section from that, calculated the rate constants. Then this is what we predict from the simple classical model for the rate constant, and these are our experimental result in the energy range from 20 to 60 millikelvin. So this is what we can access in the experiment. So this fits quite nicely, and it appears that it's really that this charge quadrupole interaction is responsible for the fast rates that we observe here. Okay. So let me now leave the field of cold chemistry and talk a bit about controlled chemistry, chemical reactions with a very high degree of control that we can perform using this cold ions technology. And we will I will now leave atomic ions behind and talk about molecular ions, because what we aim in this experiment is really to perform reactions where we control the collision energy very precisely and at the same time control the quantum states of the reaction partners very precisely. For this reason, we need to produce sympathetically cooled molecular ions which are all in the same quantum state. And this has been a big problem for the field for quite a long time, which was solved about 2 to 3 years ago by us and by other groups as well. And the method that we used to solve this problem is, so we produced, in this case, nitrogen ions again, beforehand in a well-defined quantum state using a state-selected photoionization scheme. So I don't want to go into any detail. This can be, if you're interested, you can look this up in this paper. But we can come up with photoionization scheme which produce ions in a well-defined quantum state, a well-defined spin rotational quantum state. So we then produce these ions, sympathetically cool them into a Coulomb crystal, and so we have sympathetically cooled, localized ions all in a single quantum state. So how do we know that this is actually true? So of course we have to somehow check that this is really happening. And so we have to do some sort of spectroscopy on these ions to ascertain this. And the technique that we are using is, since we're chemists, we're using a chemical technique. This is called laser-induced charge transfer spectroscopy. So the idea is that we optically pump the population out of selected rotational states that we want to investigate to vibrationally excited states of the nitrogen ion. And conveniently, nitrogen undergoes a charge transfer reaction with argon atoms if it's vibrationally excited, but not if it's in the ground state. And this is how we can detect it. So we do this optical pumping step, right? We can do this with an efficiency of about 55%, and then we see how many ions react away, depending on the rotational state that we have addressed in this optical pumping scheme beforehand. This is what it looks like in the experiment. So before the experiment, we have, again, sympathetically cooled nitrogen ions. Then we do this optical pumping, laser-induced charge transfer, and then we see that nitrogen ions react away from the center and are refilled with calcium ions. And if by comparing it with simulations, we can again figure out that about 50% of the nitrogen ions have reacted away, and this is close to the theoretical maximum of 55% that we can achieve. So for our purposes, it means that we have basically all the population in this case, the rotational ground state of the nitrogen ions in these experiments here. So it's basically a unit preparation efficiency. So what can one do with this now? So one can use this to study chemical reactions with a high degree of control. And this is what we have demonstrated in a proof of principle experiment last year. We just take nitrogen ions and let them react with just neutral nitrogen molecules in a symmetric charge transfer reaction, where the charge hops over from the nitrogen ion to the nitrogen molecule. So we have the sympathetic cooled nitrogen ions, thank you, here in the center of the Coulomb crystal. Then we take a molecular beam of neutral nitrogen, just point it at the Coulomb crystal. So the nitrogen molecules are internally cold, about 8 Kelvin, so most of the population is in rotational ground state, and the velocity of these molecules is precisely defined. It's about 800 meters per second. So what we see in the experiment is then that, okay, so the nitrogen ions undergo charge transfer with nitrogen molecules. So new nitrogen ions are generated and are then sympathetically cooled into the Coulomb crystal. So we can't chemically distinguish them from the reactant ions, but what we see is that the original population in the rotational ground state, so that we have generated for this experiment, just goes away, and we see that that we get more and more ions in rotational excited state, which are sympathetically cooled into this Coulomb crystal. So how can one understand this? So on the first side, this might look a bit puzzling if one knows a bit about the background of this reaction, because it has been known that this reaction proceeds via a linear N4+ reaction complex. So our reactants are linear, this complex is linear, the reaction coordinate is linear. So how do we get rotational excitation here of the product? Now this is where we again collaborated with theoreticians, in this case Markus Meuli in our department, who did classical dynamics calculations on this reaction. And the key to understand what is going on here is actually to realize that this N4+ complex is very long-lived because it's strongly bound by 1.3 eV. And what happens is that this binding, so once the complex is formed, this binding energy and the original collision energy is then available to, incite large amplitude motions in this complex. And this is shown here in this movie. So this complex is formed. It's highly energetic. It's dynamic. So it's by far not statically linear. And so one can see large amplitude motions are excited at some point, which you will see soon. These N2 moieties will depart again with less kinetic energy than they started off with in the collision, but with rotational excitation, like this. So this basically explains why, thank you, and this explains why we see this rotational excitation in this reaction. So what have we done here? I mean, effectively, we have studied a chemical reaction with a high degree of accuracy, and we have basically observed how initial kinetic energy has been, of the reactants, has been transformed into rotational energy of the product. And I think this is quite a nice application of this Coulomb crystal techniques, that one can study chemical reactions at this level of detail now. Okay, so just briefly in the end, I will just briefly mention a new experiment that we have set up in our lab together with Jochen Küpper from Hamburg. And so this is very fresh data now. And we also have a poster on this, so if I not make it through in the next 1.5 minutes, then I invite you to come and see the poster. So this is an experiment where we react Coulomb crystals with selected conformers of complex molecules. So first of all, what's a conformer? So we have already heard about chirality today. So conformations is another property of big molecules that one doesn't find in small molecules. So conformers are internal rotational isomers of big molecules. So let me give an example. Our favorite molecule is 3-aminophenol. It has two conformers. A cis conformer, where we have an OH group that points in the direction of the NH group in this molecule, and we have a trans conformer where the OH group points away. One has a big dipole moment, 2.3 dBi. The other one has a small dipole moment, about 1 dBi. So why should one be interested in this? I mean, conformers are the dominant form of structural isomers in complex molecules. And for complex molecules, they govern the chemical reactivity of the molecules. So real chemists like to call the steric effects. But the problem is that these conformers are very often energetically close, and there are low barriers in between them, so they often easily interconvert between one another under ambient condition, and so it's difficult to study them. So what the guys at the Fritz Haber Institute in Berlin came up with is a method to select conformers of large molecules in the gas phase. So we have a molecular beam containing a molecule with several conformations. It traverses through an inhomogeneous electric field. The different dipole moments of the molecules then cause different stark shifts. So basically the two conformers in the beam are split apart. So we get a spatial separation of the conformers. And what we then did in our experiments is we just put an ion trap with a Coulomb crystal at the other end, and then pointed the molecular beam containing the right conformation at the Coulomb crystal and looked what was going on. And when we can see then this kind of reaction profile, so this is a reaction rate constant as a function of the deflection coordinate. We have here the region where mostly the trans conformer reacts, here mostly the cis conformer reacts. And if we quantitatively analyze this, then we find that the cis conformer reacts twice as fast as the trans conformer. So if you're interested in the explanation, then please do come to our poster. And here I'd like to skip the summary, and I'd like to acknowledge the help of all the people who contributed to this. So the main students behind this were Felix Hall and Daniel Rösch, and our postdoc Xin Tung, who were really the driving forces behind the results that I've shown today. Our collaborators, Olivier Doulier, Markus Meule in Basel, and Jochen Küpper in Hamburg, our funding agencies, and you for your attention. Thank you very much.
Okay, thank you very much, Stefan, for this great talk. Obviously, I find it great, of course. And who has questions? Okay. So I start with Alexei.
So you discussed this translation to rotation transfer, motivated by sort of some discussions we had with Paul and others in the past few weeks. Have you seen the other way around, rotation to translation transfer? Can you study this, or?
In principle, we could, but the experiment was framed in a way that this can't happen because we are rotationally cold to start with. Yeah. So the ions are all in the rotational ground state in the beginning, and the neutrals are 50% of them are in the rotational ground state. And
but you could set up it somehow cleverly the other way around, so that maybe you still.
Yes. So we could put more rotational excitation in the ion in a well-defined way, and then we might be able to look at it the other way around.
In the calcium plus rubidium system, how was Rb2 plus produced?
Yes, this is a good question. So back to this mass spectrum. So yeah, we see this peak here, and this is identified with rubidium 2+. And there, in principle, we can think of three processes that lead to it. So one is a consecutive reaction of calcium rubidium plus with rubidium. At the moment, we think this is the most likely option. Then there is also the possibility that we have rubidium 2 in the mod by photoassociation, which is then ionized somehow. But in a rubidium-87 mod, it has been shown that this doesn't happen very effectively. And the third possibility is that we form rubidium ions, obviously, in this process, right? And then we have rubidium atoms in the mod, which are laser cooled. And we could, in principle, have a radiative association of excited rubidium atoms with this rubidium product ion. So this is the third possibility. And no. So the first possibility is energetically feasible, that we know, and the third possibility is we have to look into this into more detail. The second possibility is very unlikely.
So I'm wondering about the role of many-body physics in this problem. If there is any role, it could be classical many-body physics, that's fine, but you have these crystals. Yep. Does it matter that you have a crystal? What's the role of the crystal? Everything you presented, from what I saw, was two-body. Mm-hmm. And you also have spatial non-uniformity in your images, and some dynamics happening in your images. Mm-hmm. And if you average over many images from the noise on these images, you can pull out some information classically as well as quantum mechanically. So I'm wondering if you've thought about the many-body properties of what you're seeing.
Yes, I mean this is an excellent question actually. So for the ions, I mean the ions in the crystal, they are about 20 to 30 microns apart. Yeah, so it's the distance between them, so we don't expect to see any distinct many-body effects there. So what happens in these sort of experiments, and I think Johannes will talk about this a bit later, is that one can have three-body collisions. Yeah, and in our experiment, this doesn't play a big role because the rubidium density is very low, on the order of 10 to the 8 to 10 to the 9. However, if one goes to BEC experiments, then these seem to become important. So this is the sort of at least three-body processes that become important in these kind of.
Okay, what's the screening length? The Coulomb screening length in your system? You said 20 to 30 microns means that many body features don't matter.
Yep.
What is the screening length? Because that's what would determine whether sort of many body correlations can build up, right?
I wouldn't notice at the top of my head.
Okay.
Yeah.
Maybe we'll talk more later, yeah.
Yeah.
Any other question? Yes.
You mentioned the N2 plus reaction with argon that goes on only when the N2 plus is vibrationally excited.
Mm-hmm.
It goes also the other way around. Argon plus N2 delivers N2 plus in the vibrationally excited state V equal to 1 or
Mm-hmm.
higher, depending on the collision energy. I wonder what is the state-of-the-art explanation actually of this kind of population inversion?
For argon plus
for argon plus N2 or the other way around? It's bound to be the same explanation, I guess.
Yes, there are. There is some recent experiments by Roland Wester on this actually, on the argon plus N2 problem. Yeah, and this of course it boils down to a curve crossing problem again. Yeah, and then it's a question of Frank-Condon factors, right, at the relevant crossing points. Yeah, this is the short version of the story.
Okay, Stefan, if I have a question about the control over the collision energy. In your Coulomb crystal experiment with the cold neutrals, it's only the micromotion that gives you some control over the energy, is that right? And you're controlling that through the density by putting more ions in, it moves out to higher energy. Are there other control tools? What are the control tools you have over the collision energy distribution?
So we have two types of possibilities to change the collision energy. So in these experiments, we just do it by the size of the crystal. And what we basically do is, in this way, is we shape the collision energy distribution. Yeah, because with big crystals, we have more ions with a high kinetic energy because of micromotion. So basically, the collision energy distributions, they peak at the higher collision energy. So this is what can be seen here. So this is what we do in these experiments. And in the other experiments with nitrogen, so what one can do here is, so all the nitrogen ions in this case are actually lined up on the symmetry axis of the trap. And what we do is we just apply a static offset field then and just move the whole crystal off axis. And in this way, the string of nitrogen ions here in the center is moved away from the axis and gets micromotion. This is actually a much more precise way of doing it than just with a big crystal, and this is the method of choice here for these types of experiments.
Yeah.
You mentioned these non-adiabatic transitions. I was wondering if you have some feeling for how large those coupling matrix elements. Presumably this is due to spin-orbit coupling, right?
For the non-radiative charge transfer.
Right.
Yeah.
And what would be roughly maybe the probability of those transitions when the population get close to intersection?
Yeah. So these couplings are very small. Yeah. So I couldn't tell you the absolute magnitude, but I mean
few wave number, I think.
Sorry?
Few wave number.
A few wave numbers, yeah. Yeah.
Very small.
So basically, they give rise to rate constants on the order of 10 to the minus 13. Yeah, and Langevin is 4 orders of magnitude faster. So it basically only, every 1 in 10,000 collisions then leads to an event.
Stefan, do we have to go to the poster, or can you say something about the cis-trans symmetry already?
I would of course prefer if it comes to the poster, but I can say a bit about it now. So I think so. We are still analyzing this at the moment, but we think that the reason is again that the cis has a higher dipole moment than the trans, and this then translates into a higher collision rate. And this and the reaction it actually only happens out of the excited state of the calcium, seems to be collision rate limited, and the collision rate is just higher for the cis than for the trans by about a factor of 2.
Okay, if there is no any further question, right, so let's proceed to the next speaker. Thank you, Stefan, again. So the next speaker is Tim Stoffley, and we'll still hear about cold chemistry, with molecular ions and new techniques in this perspective. And again, I will be as strict as possible, yes, with the time. I'll show you sign.